In each of these videos, I want to introduce a few kind of puzzles which you should be able to solve within a few hours, and also a puzzle which no one has ever solved, ever. And so I'm talking about maths problems, basically. But the kind of mathematics which is going to be involved is not going to be kind of difficult maths. I'm not going to discuss anything which requires anything more than like the kind of mathematics that a 16-year-old should know. So without further ado, let's have our first puzzle. This is one which I think I first heard when I was about 7 years old. And it goes like this. Draw a house without taking your pen off the paper and without backtracking. So let me show you the kind of house I want you to draw. I'm not going to show you the answer. So there you are. Try and draw a figure like that, but you're not allowed to lift your pen off the paper and you're not allowed to backtrack. So see if you can do that. Now, what this actually is an example of something called a graph. Let me just add a couple of features to it. So you see I've added these dots. So now this is what we call a graph. A graph is a really, really simple thing. It's basically just a load of dots connected by lines. In fact, I think that graphs are really one of my favourite things from maths because they're just so simple on one hand, but there's so many things that people don't understand about them, and they're so important for so many areas of science and whatnot. So a graph, aka a network, here's an example of it. It's a load of dots connected by some lines. The thing is though that the actual geometry of the thing isn't really that important. We can think of these lines as being made out of string or something, so we can move them around and it's still the same graph. So for example, this is sort of exactly the same graph as far as we're concerned. Because, I mean, it looks slightly different geometrically, but everything's connected up in just the same way. Similarly, this graph also at the bottom here is equivalent. So if you want to know if two graphs are equivalent or not, think of these dots here, these nodes if you like, think of them as little balls, and think of these lines as bits of string which are stretchable. And if you could sort of manipulate all these balls tied together with these string so that one structure looks like another structure, then those two graph structures are equivalent, okay? So this is the one nice thing about graphs. If you can't draw very well, it doesn't matter. All you have to do is connect things up in the right way. Okay then. So puzzle number 2. This is a bit more challenging. So now, instead of drawing that house shape without taking your pen off the paper, the problem is to try and draw this shape here. Without taking your pen off the paper. So you can have a go at doing that, and if you can't do it, then try and think of a reason why. I mean, it's one thing to say, oh well, I tried 100 times and I was not able to do it, but try and come up with a reason why you can't do it. If you can't, maybe you can. Have a go. Okay then, so now we're getting close to our unsolved problem. So the problem I want to talk about is counting how many different graphs there are. So we're just going to talk about connected graphs, okay? So like this graph here is not connected because there's no way to get from here to here, okay? So we'll just talk about connected graphs. And the problem is to count how many different graphs there are, up to 4 vertices, okay? Up to 4 nodes. So how many graphs are there with one node? Well, it's just one, just this one. So that's for 1. How about 2? How many different graphs are there with 2 different nodes, connected ones? Well, there's actually just one, isn't there? That's the only one with 2 nodes. How many are there with 3 nodes? Well, there's actually 2. There's 2 fundamentally different graphs with 3 nodes. How many are there with 4 nodes? This is taxing my... Can you see this? So we can have one like this. And one like this. And there are various others. So my problem for you is to find out how many graphs there are for 4 nodes and for 5 nodes. How many fundamentally different connected graphs. Okay? So that's the challenge, and that hopefully you'll find this kind of fun. When you start getting into it, it's actually pretty interesting because you see all these funny kind of shapes, and you have to kind of you have to keep quite a lot of things in your head because you have to be able to recognise when you're going to draw the same structure twice and think of some kind of systematic way to enumerate these different graphs. Okay, so what's the open problem? What's the problem that no one's ever solved? Well, that problem is to find out how many graphs there are on a general number of vertices. Okay, so if I give you a number, say 110, can you tell me how many graphs there are with 110 vertices? Can you find a formula which tells you how many graphs there are with a given number of vertices? Can you find a pattern in the numbers? So the pattern starts with 1, that's the number of graphs there are on one vertex. 1, that's the number of graphs there are on 2 vertices. 2, that's the number of graphs there are on 3 vertices, and so on and so forth. But what's the pattern in general? And this is a completely open problem. People have approximations. They have kind of a rough idea how many graphs there are with a certain number of vertices, but they don't have an exact formula. And people have worked on this a lot. And, you know, the basic ideas at play here are nothing that a 4-year-old couldn't understand. But people haven't been able to find the answers. So good luck, folks.